We'll move on to our next session by Mallikarjun. Mallikarjun is an engineer by heart and profession, focuses on building customizations on top of HBase to support multi-tenancy and HBase committer at Flipkart. Today, he'll be talking to us about our journey to make HBase truly multi-tenant while managing primary stores for some of our most critical services, and also talking about the challenges faced and our attempt to solve them. Let's have Mallikarjun on screen.
Hey, hello. So I'm Mallikarjun. I work at Flipkart, and today we'll be talking about our journey to run HBase as a multi-tenant and what are the challenges we faced and how uh, what are the solves we have and so on and so forth. Right. So this is going to be the outline. We'll talk a bit about HBase architecture for those who are not very familiar with it, and we'll be talking about the problems and like how we approach to solve them. Some of them. Right. So to give perspective about how what we do, so we primarily saw use HBase for OLTP based transactional workloads, and some of the very highly critical workloads at Flipkart like payments, order management systems, some user facing services, sessions, games. So several of them run as tenants on these HBase clusters, and they are of diverse workloads and storage needs. And about the scale, you can see that we have around 100 tenants, and we are running on around 8,000 plus virtual cores. And during last big billion days, we reached a peak QPS of a million read place write in 1:1 ratio, but we are capable of serving way more than that. You can see one example where one of our tenants with the 30 node cluster was able to scale a million QPS, read QPS with very good tail latencies, right? And to give about a bit about to talk a bit about architecture, HBase architecture, for those who are not very familiar with it. So you can see there are two layers. One being the serve layer, that is the HBase. One being the storage layer, that being HDFS, right? And the client-facing nodes are called region servers for the serve layer, and client-facing data layers called data nodes. Right, so these two are co-located on a single machine, and you will have multiple of them. And some important features of HBase: it's strongly consistent, auto failovers and recoveries, horizontally scalable, and so on and so forth. And if you see on the right side, you can see how the layout is, the data layout is. Uh, uh, Table, which is corresponding to like any other data store. A table is further split into regions. Each region is can be independently hosted on a region server, which can serve independent of the state of other regions. And each region is further divided into column families, and each column family stores in multiple files. Ideally it will be one file, as you keep on writing you will have multiple files. Using compaction, it will keep on compacting and reducing the number of files. And region server is a server process which hosts the regions, and data node being the one which hosts the data. Right. So some important terminologies. Favored node is an indication to HDFS to specify where do you want to place your files. Say if you want to place it in HDFS, and you have a replication factor of 3, and you can specify to HDFS saying these are the 3 nodes on which I want my data to be sitting. That's what is a favored node. Region server grouping being a group of nodes which are a group of region servers which are bounded by a namespace on which tables on which you can have tables with namespace around it, right? And write ahead log is a append only file system, which is probably equivalent to a bin log in a SQL or a MySQL terminology, which is used for recovery purposes and is being written. So these are some of the terminologies. And so by tenancy multi-tenant, what do we mean by that is, if you look at this diagram, so there are 3 layers. There are 2 layers, right? So one being the serve layer, the other being the data layer. So you can see RS, that is the region server, which is the serve layer, and DN being the data node, which is the data layer. In data layer, there are two parts. One of them is a wall, the other one is actual data that is going to be storing your data, right? And you can see there's a table A and table B. Table A is sitting on tenant A in terms of serve layer, in terms of data layer, in terms of walls. And if you look at tenant B, and it is hosting table B in serve layer, data layer, as well as wall layer. So this is what is a perfect isolation. This is what we can expect from as the end goal with what we wanted to achieve. So apart from hosting these two, CPU, memory, disk, all the resource utilization should be dedicated to the tenant which the node is allocated to. Right, that's the end goal of us of the multi-tenant HBase. We'll talk about problems we faced while running as a multi-tenant system. First problem being data, right? So if you look at this diagram, similar to what we had in the previous slide, you can see that the serve layer is perfectly isolated. You can see that the pink ones are on the tenant A, and green ones are the tenant B. But if you look at the data, there is it is bit of here and there. So in HBase, data layer is treated homogeneous by default. It is treated homogeneous, and all of the nodes are equal. So data can be placed anywhere to anywhere. There is no isolation provided for that. So, if you look at what HBase provides and what is possible, so what we want is, say, each tenant having their own set of requirement, their own workload, their own hardware requirements correspondingly, right? So, if you look at tenant A, he wants to run it on 8 core, 40 gig RAM, and SSDs of 1 TB. And if you look at tenant B, he wants to run on 24 TB of HDDs, right? Maybe tenant B has a lot of disk requirements, and tenant A has very small, but he wants higher throughput, right? But what is possible with HBase is either you have to go with since the data is all data nodes are considered homogeneous, so you have all of the data nodes will have to have of same disk size, right? Otherwise, you will see one is on 90%, one is on 30%, and so on. And if you look at either we go with 24 TB HDDs, or you go with SSDs, which are of high number. So both of them is a compromise. If you are going with HDDs, then tenant one throughput requirements might not meet. If you go with SSDs, then you will have to pay a lot more price to get such huge number of SSDs for serving both of them. So a bit about how we approached on a background for that is, so one concept in HBase is load balancer, right? So primarily load balancer does two functions. One being distributing ensuring the optimal resource utilization across the region server. It could be that you have regions being skewed, or it could be that you have, say, data locality being not up to the mark on certain region servers, or it could be rack awareness. So it ensures that all of these parameters, whatever is configured with balancer parameters, all of them are ensured in a optimal manner, so better utilization of resources. That is one of the functionalities of balancer. And second thing is that it assist assignment manager. So what assignment manager does is, as I told, there's a concept called region, and each region can be hosted on its own region server, on any region server, and it is independent of other regions. So these regions can be moved around for optimal resource utilization. So assignment manager does the assignment of regions. Say, if you want to move region, say when a table is getting created, you have a lot of regions getting created. So these things will be assigned to specific region servers. So that's what assignment manager does. And some of the scenarios when regions are getting assigned is, say, a table creation, split and merge, auto split or manual split and merge, when balancer tries to balance it out, or when there is any change in topologies, say for example a region server going down, or so on and so forth, right? So these are some scenarios where you'll see regions being moved. And so how we approach the problem is, so there are some load balancer which comes with HBase, and some of the ones which I'm interested to talk about in this, because we use them, is are region server load balancer and favored node stochastic load balancer. So what region server load balancer does is, it will ensure that all of the tables for specific RS group are being assigned to the same. So it ensures the isolation in terms of servlet. That is one of the goals of load balancer, RS group based load balancer, along with other responsibility that it has. So what favored nodes stochastic load balancer does is it will create favored nodes for, say, a specific region, so that uh, for a specific region, data is going to be sitting on some specific nodes, so that you can get a better locality. So these are two functionalities. But if you look at what happens when when a table is getting created on a favored node, a client requests master for create table, and master creates regions and asks assignment manager to assign it. Assignment manager asks load balancer for various things, and during that time, what load balancer does is it will create favored nodes, and then after that it will store these favored nodes in meta tables, and then it will say everything is done. So tables is getting regions are getting assigned. We tweaked that a little bit. What we did was, instead of generating favor node at random, what favor stochastic load balancer was doing, we ensure that these favor nodes are chosen only within the region server group that this table is residing. Right. So how do we know that? So the region. So this in this context, say, a region will have the understanding of which table it belongs to, and table will have understanding of which RS group it belongs to, and all of the region servers which are part of this. And this, if you see, we chose. You can have several strategies. One being randomly assigned, and there could be like least used and so on. So we chose to pick favored nodes which are least used, as well as being rack aware, and all of those constructs we put in place, and that's how we ensure that data is going to region servers are going to pick favored nodes only. Regions are going to be only for the region server group that it belongs to. So this is one part of the problem, right? So where you have favored nodes being stored in meta for every region. Every region has as many replication factor favored nodes as it is there. So you're going to store it. And second part of the problem is, when do you use this? So when do you use this? When do you pass this information favored node to HDFS layer is, you have, there's a concept called memstore. Memstore is the data in memory for a specific region hosted on a region server. And when a new request comes, data is put in memory, that is memstore, right, for that particular region. And once a memstore reaches some threshold, or there's certain criteria is met, it will be flushed to disk. At the time of that store file writer, it will fetch the favor nodes from meta table for that particular region if it is available. If not, it will do what it is doing, just randomly spread over the HDFS layer. And then after that, it will pass this information favor node to the HDFS layer, and HDFS layer will do the rest. It will ensure that the file that that is getting created is hosted on these particular favored nodes only, right? And that's a best effort strategy, and we'll talk about why and so on. So the results were very good, and you can see that on the left side, say, there were different regions of tenants, and each tenant is having correspondingly assigned based on their sizes. And on the right side, you can see that whatever we wanted to achieve with respect to data isolation, we were able to achieve. But this post that, so we ran into a few issues. One with respect to skewness, the other one is data spillover. What skewness is not really a tenancy problem, but which was resulted out of the solve that we did in the previous step, was resulted into skewness. So why skewness happens is, say, if a node goes down, a topology changes, and so on and so forth. So which was resulting into not a balanced assignment of favored nodes, right? So only regions moves on certain criteria, not all the time. So it was creating skewness. We'll talk about those details in a bit of time. And you can see here some nodes are hosting, say, 3 4 blocks, and some hosting 1 block, and so on and so forth. And very, very few block spillovers cross tenant, which is not happening like it was happening before random. Now it's happening very few spillovers, right? So with that, we'll go to the next problem we just spoke about. So I'll give a bit of a background on balancer. So what balancer does, a bit of internals of those, right? So one concept is, there are a couple of concepts here. One being a cost function, the other one is candidate generator, which is very important to know about a balancer. right? So what balancer does is it'll create a virtual state of the current existing cluster, and then it'll identify the existing imbalance and then see where should I balance or not. If it's already balanced, then it will not do anything. If it is not balanced, then it will go to the next step. So what happens from next step is, so we'll talk about these two concepts that we spoke about. One being the cost function. What cost function does is, there are, like, I think several cost functions part of which are configured as part of default balancer. What cost function does is, you say, for example, if you have a locality based cost function, so it will give a cost between 0 and 1, 0 being that it's perfect for this particular aspect. So if you're talking about locality based load balancer, then locality is very good. All of the data is hosted on the same node and you're serving it very well. And second example is region skewness. If all of the regions are assigned in a homogeneous manner, as in, like, there's no skewness, then it's going to give cost of 0. On the other side, if it is highly imbalanced, then it's going to give a cost of 1. So overall cost is sum of all these costs that are generated by individual functions along with their weight, is what is the overall cost. And if overall cost is beyond certain value, then balancer will run the balancing, right? And second concept is candidate generator. So balancer runs for a predefined number of steps. I think by default it's a million number of iterations. And each iteration, what it does is it'll pick a random candidate generator. Here again, there are a lot of candidate generator which are coming registered by default. And I'm talking specifically about stochastic load balancer. This is what is used across all the balances which I spoke about. Right. So what candidate generator does is, so if you're going to invoke locality based candidate generator, it'll give you an action. An action is move region A from region server A to region server B. So that will reduce the cost. That probability of reducing the cost is high based on as per that candidate generator. If you're talking about region skewness candidate generator, then it will pick a region which can help you balance the cluster more. So on each iteration, it will pick a random candidate generator. It will tell the candidate generator that gives some action, and load balancer will apply that action. If the cost is reduced, then it will be hold on. Otherwise, it will revert it and move on. After all the iterations, it will check if overall the cost is reduced. Then this is a new layout that the balancer has to apply. If it is much worse than what the cost was earlier, then it is not going to apply. So this is how balancer works. And the second concept is data spillover. So if you look at left side, so pink blocks are serving layers, and blue blocks are secondary and tertiary copies of data, which is not really serving; it's just a copy of data. And on the right side, if you see, there is one node, that is region server 1 is dead. So once it is dead, assignment manager will make sure that region 1, which is serving layer, is moved on from that to, say, region server 4 or somewhere else. So this ensures that all of the serving layer is fine, but the favored node is still associated with region server 1, which is dead, and HBase is not going to do anything about it, and which can result into data spillovers, because HDF is trying to assign blocks of data with respect to region server 1, which is no longer there. So with respect to the problem statement, again, continuation of the previous slide, previous problem statement, there are two things: spillovers and skewness, and I spoke about this. So what we did was we wrote a couple of cost functions, a couple of candidate generators. So one cost function is dead node cost function, and on the left side you see that. So on the left top you see that there are no dead nodes. So that cost function will cost 0 because everything is all right. On the down, if you see, there is one dead node and there is one copy of data is allocated to that. That will give you a higher cost, right? Higher cost means that there's higher probability of your balancer being triggering the balancer, and there is if you associate some weight to it, you can give much higher value for a specific cost function. On the right side, if you see imbalance, on top right, you can see that there are copies, say RS1 and RS3 is having one copy, RS2 is having 2, and RS4 is having 4. It's even if you change a bit, it's not going to give you a very good balancing, because it looks more or less balanced. So you give some cost to that. and we use standard deviation to understand how deviated a particular node in terms of secondary copies from others. And if you look at the below one, you can see that it's highly imbalanced when you give a higher cost. So with this, as I told you, give more cost, then you will have more probability of trying to reduce the cost and hence more balancing. So about candidate generator, if you look at the same diagram on the left side top, you see that there's no dead node, so no action. If you look at below, there is a dead node. So what it does is it'll give action saying move a replica 2 from region server 1 to say region server 3. That is the action that it will give. That has the probability of reducing the cost, right? And similarly on the right side imbalance, if you see on the top everything is fine, no action. On the bottom, if you see it's imbalance, so one possible action that imbalance candidate generator can do is move replica 3 to replica region server, from region server 1 to region server 2 to region server 1. So that could help reduce the imbalance, right? So with this we were able to get very good results, right? And some learnings out of this is one being that if you have too few regions per region server, then it was giving, as I told, we use standard deviation, it was not going very good results, because one region here and there could have high cost generated that could trigger balancing and was not doing very good. And second thing is these favored node is only applicable when a file is getting created, not for the existing blocks. So when a major compaction runs, we were able to restore all the data in the correct place. Until then, if there is a change in topology and so on, it was being okay. But we run major compaction for various other regions for performance, for improving the say several other benefits like so data locality will be improved, TTL expired keys will be removed, and dead or remove rows will be removed, and so on and so forth. So we run major compaction every day for a lot of our tenants, sometimes once in 2 days and so on. So that was perfectly fine for us. And the other reasons, other places where it did not work out for us was if HBase sees this node being up, but HDFS considered this node as dead, say for something like disk read only, disk corrupt, disk is full, decommissioning, and so on. So, which was very marginal number of scenarios which can result into this. So the next problem statement will move on to wall isolation. I spoke about data isolation. Now we'll be talking about wall isolation, right? So what happens in HBase when you are going to make a put or some mutation? This is what is going to happen. So a client does a put, then it is written in two places. One is in memstore, the second one is wall, right? So right ahead log I spoke about a little while ago. So wall is up and only file system. Each mutation is recorded as an entry, as a wall edit in the wall, and as it reaches some threshold, it is going to be rotated. A mem store, again, as it reaches some threshold on certain criteria is met, then it will be flushed to disk. So since wall is written to disk in a synchronous manner and data is kept in memory, if a region server goes down, say before the data is flushed to disk, then walls are used to recover the data, and that is one of the purposes of wall. There are other purposes like replication and so on. So recovery is one of the primary reasons wall is there, and this will give high throughput because writing a sequential file system on a file is much faster than doing random, right? And if you see again, expanding the previous diagram, you see that we have added wall as one block, and here again walls are data layer is considered uniform, and which results into again so blocks moving here and there. So which is a bit of a problem, because if you want expect some certain throughput, you're not going to get, because you the disk is of another tenants, which could be slower, which could be whatever, right? So we applied very similar strategy as data. When a wall gets rolled over, wall we choose favor nodes. When we are writing a wall to DFS layer, we are going to choose favor nodes based on the region server group that this particular region belongs to. So walls by default are one per region server, and if you have, I'm not going to get into multi-wall. We're not using in that fashion. So one wall is per region server, and so you identify that, and then so on. So which again gave us good results, and we were happy with it. And another thing is there's no problem of skewness, or there's no problem of spillovers like earlier, because walls are short lived and they're going to get created every often. Especially if you're right heavy, you're going to create it more often, right? So that makes it, even if there is a change in topology, one file here and there is not really a big concern, right? So that being the data part, the second part is replication. So change data capture. So change data capture we'll talk about. Before that, I want to talk about replication, how replication works in HBase. So what happens? So we use so HBase uses wall for replication, and as and when there's a wall log role, that is new file getting created, it is put in a queue, and there's a concept called peer. There's a corresponding concept called shippers, right? So peer is nothing but, say, if you want to replicate it to two different clusters or any other replication endpoint, then each of them is registered as a peer, and you can see it from HMaster UI. And this shipper, what it's going to do is, when a log file or when a wall file is available, it's going to batch events and then invoke the replication endpoint with the replicate method. And replication endpoint is nothing but endpoint for replication, right? So HBase cluster replication also does very similar. If you want to have your own replication, then you can implement replication endpoint, and then you can have a method called replicate, which is invoked with batch entries as and when there's new data available, right? So what is change data capture? What do you say? You have several side effects that you want to have from your data that is being generated in your database. One thing could be that you have a secondary database which you want to fill it up, which has different read write patterns, which can be used for other use cases. You want to fill it up from your primary store. Second thing could be that you want to run a distributed transaction, which you want to pass on your state changes, and so on and so forth. So there are a lot of side effects which you want to. So this change data capture is one way of capturing the changed data and then propagate into secondary use cases. Another thing is, with respect to change data capture, is isolation. So we are in the concept of multi-tenancy. So this isolation is very important. So along with change data capture, we want to give the isolation. Right? So what we did was, so I spoke about source shippers a bit ago, and we wrote our own replication endpoint for Kafka, and we have one for Pulsar as well. And so these replication endpoints implement replication endpoint, and then once there is data available, it's invoked with batch of edits. So each wall edit has details of which column family it belongs to, which column family this data is, what is a table, and so on. Using that, we'll be able to find corresponding details that you want to ship to. Say, if you are using Kafka, which topic it is, where do you want to ship, and what are the details. And that is as part of packaging that we have. Say, for each, at the time of each region server creation, you're going to specify what region server group it is, and there's a lot of configuration that comes as part of it, and so on. So with that, we'll be able to identify. And when you do all of these batch edits, processed, send, ship to outside, you can say this entire batch is succeeded. Or if it is failed, it's again invoked with the same batch. If it is succeeded, then it will pass on to the next batch if it is available. So one small concept I want to highlight is, so when a put happens, a wall edit is going to get generated. So there's some meta information that is stored, is which clusters I have seen. Each HBase cluster is identified by unique UUID, and you can see that. When a wall edit is getting recorded, it records that which cluster I have seen. When you replicate it to another cluster, it again says that, okay, I have seen this cluster too. When you replicate again, it says I've seen replication, I've seen cluster 3. And when this will avoid loops. That is one. But more importantly, we use this concept in our change data capture to provide use cases like when you want to take the data, say you have active on two DCs, you want to take data out in both the DCs, then, and each of these are cross replicating. You don't want all of the data to be passed on both the clusters. You want only the one which you want the generated on the same cluster. This is one way we have identified. Or you can take out all of the data in one side, or if you have multi DCs, it will be a lot more useful. So this is one thing that we did as part of this. So that being wall, sorry, change data capture. And second thing is about replication is cluster replication, right? So you have two HBase clusters, you can replicate asynchronously using HBase. So what HBase does is, if you look at the left side, what HBase does is, so as you have as you have wall edits, a batch of wall edits being shipped to other cluster. So what it is, each region server, when it is shipping, it'll randomly pick a region server on the destination cluster, and then it could be your tenant, it could be outside tenant, right? Which is again breach of isolation. Even however small the CPU is, it's breach of isolation. It picks a random region server and then gives the batch of edits. That region server will identify in the cluster, in its own cluster, that which ones I should assign, or which one owns each of the wall edit, right? And what we made this change to ensure that there is RS group understanding of it, so that the data is written to the same one of the randomly picked one of the region servers on the same RS group, and that ensured that we were able to provide the isolation. And obviously we made it configurable. You can choose whichever you want based on the use case and so on. And another thing is, a lot of our use cases come from already existing HBase clusters, so they want to migrate to as part of tenant. So then a problem comes is export snapshot. That how do you migrate this? So when you are migrating the data to a cluster to which is multi-tenant, then what happens is there is no awareness of tenants for with export snapshot. It can write to any files which can fill up the disk if you're writing a huge amount of data. Again, we brought in the concept or understanding of RS group, and with that understanding, what happens when each split in the MapReduce job, each split is writing the data. It figures out which it takes as input which RS group you want to write to, and then it figures out from the destination region server, zookeepers, which all the region servers belong to that particular RS group, and then it is going to write only on those nodes, and this gives the proper isolation for us. There's no breach of tenancy there as well. And third thing is backup restore. Again, backup restore does not have understanding of RS group, which resulted into some problems written here. So there's a concept called wall cleaner when when a backup there is full backup, there is incremental backup. Full backups are based on snapshots. Incremental backup is based on walls, write ahead log I just spoke about, right? So these walls are accumulated if backup did not happen, backup failed or so on for a longer duration. As and when backup is taken, then wall cleaner will go and clear up the wall logs for which backup is taken. And with this, the problem is that either you have to have backup for all of the tables, because otherwise walls are not going to get cleared up, or none of them, right? So which again breaches the multi-tenancy. If one table is configured in a tenant for backup, the other tables are not configured, then it's going to retain forever. So we brought in this understanding of RS group in wall cleaner as well. So this ensure that if one RS group tables are configured with backup, the others are not, then it will clear both of them. One, it will clear when backup is done, the other it will clean up whenever it is running. So that sums up all of the problems that we have listed on here. I'll just go over the summary and then share a bit more details, right? So I last few problem statement I did not go into too much detail in the interest of time. So we'll be writing a tech blog. You can watch out for spacetech.flipkart.com. So it might be available in a few weeks, right? On the summary, so we solved data isolation using favored nodes, and then skewness and other problems arise because of that. We solved with cost functions and candidate generator. Wall isolation, again, we solved with favored nodes. CDC, we implemented our own, and then our packaging, which took care in terms of the isolation that is required, and cluster replication. Other three, we added RS group support. Yeah. So now I can